Hi everyone. So myself Maria Rubiston, Assistant Professor, Department of EC S.A.E. Engineering College, and I am welcoming everyone for today's GATE session, and especially we are going to discuss about second section of EC syllabus, where we will be going to discuss about Z transform. And basically we discuss about continuous time signal and discrete time signal, and most probably discrete time signals are highly concentrated for doing many kind of applications, especially for image processing, filter design and other things. So the same thing can be done by discrete Fourier time transform also, but whereas somehow discrete time Fourier transforms are converges with some drawbacks that can be overcome by Z transform, because discrete time Fourier transforms are especially used only for infinite interval. But if you want to find out the finite set of data through any kind of signal processing, we should depend upon Z transform. So there are certain feasibilities and features where we can deploy Z transforms are. So first one we see about frequency response. So if you want to find the system to be stable, or if the system identification can be done in a better way, that can be done only through the frequency response characteristics. So it will always give a maximum efficient output about the system. And next is about the stability analysis. So when you are designing a system, stability is always a major constraint, where in this part with respect to Z transform, stability criterion can be characterized by region of convergence. So when we are designing a system, so when we force some input to the system should give a response accordingly. So if the output is predominantly depends upon the input, so we may achieve a good stability on the system. So that characteristics also can be done by an Z transform. And next is about finite length analysis. As I said, like the advantages of Z transform over discrete time Fourier transform is we can design a application for the finite set of interval. And next is about complex variable theory, and later we are moving on with deep learning or machine learning. So that kind of analysis we should depends upon the variable based analysis, so where we can go for a complex variable theory. And next is about how Z transform is far better, or it can give a better efficiency over discrete time Fourier transform for signal processing or signal analysis or any kind of image processing applications. So for that purpose we should go on with the Z transform. So these are all the listed applications where the Z transforms evolves. First one is about mathematical and signal processing, and signal processing is very important nowadays, because when we see for medical application, while capturing some images with respect to any disease parameters, the signals are predominantly taken by means of electrodes. So where fetching the information from the electrode, which will give a biological signal, it is purely an analog in nature. But if I want to perform those signals by the system, we should convert them into a mathematical expression. So for that, if I want to perform a signal processing, I have to combine all the application of signal pattern into a mathematical expression. And next is about digital filters. So filters are very much important for any kind of communication system, so where it plays a vital role. And next is about linear discrete time systems. So generally linear is nothing but it should exactly give an output based on the given input. And next is about system design and analysis. So before designing any system or before deploying any system, we should know what kind of the input parameter the system will accept and how far the system will give a performance. And next is about telecommunication automatic controls. So normally when you see for a telecommunication application, signal routing, signal processing, signal switching, where the properties of the signal comes into picture. So accordingly we can shift the signal from one place to another place. And when we exactly are discussing about Z transform, we should know there are two types of transform in it. One is called Z transform and another one is called like an inverse Z transform. And these two patterns are very important while expressing a signal in terms of a mathematical model. So the expression, and whereas in the Z transform formula we can segregate these two into two patterns. One is called bilateral Z transform another one is called like an unilateral Z transform, and these two things are differentiate with each other by means of setting the limit values. When we see for bilateral Z transform, the limits are lies between minus infinity to plus infinity, where summation is denoted by we have more number of samples in it. Since we are describing everything in a discrete manner, in the discrete signal we have multiple number of signals. So if I want to estimate or if I want to calculate the processing time, or if I want to process those signal, I have to add everything in such a way. So I will be using for a summation. So summation n is equal to, so where x of n is nothing but an input signal, where z denotes the z transform. When I take z transform of my x of n, it will give summation n is equal to limits are lies between minus infinity to plus infinity, followed by your input signal x of n, then you are taking coefficient of your z by z power minus n. Similarly, the same pattern can be conversed like an unilateral z transform. So x of z is equal to z transform of x of n, where we are looking for either the limit from minus infinity to 0 or from 0 to infinity. So 0 to infinity x of n z power minus n. Similarly, if you want to calculate inverse Z transform, generally inverse Z transforms are used to identify the system performance, or if you want to find the response of the system, or system output response, or if I want to calculate the impulse response, it will given most predominant factors over there. So if I want to calculate inverse Z transform, where x of n is nothing but your input, when you take the transform of your x of n, it will be in another format. So initially x of n may be a discrete set of value, or it can be a graphical representation, or it can be a matrix format for an input of any kind of the system. After processing, and the information can be conveyed to a system to some output devices, but the output devices will not understand the data processed by the system. So we have to convert the understandable format for the system. So again we have to reproduce our input. So how the inputs can be reproduced? So that can be done by your inverse Z transform. So x of n will be equal to z power minus 1 will indicate inverse Z transform of the transformed input x of z will be equal to 1 divided by 2 pi j closed integral of x of z power n minus 1 and dz, where c is nothing but the counterclockwise closed path encircling origin and entirely in the region of convergence. Because from the beginning of the slide itself we discussed how the Z transform will confine the stability of the system, because we are finding the values for the finite set of intervals. So region of convergence is one kind of a factor which will determine how my poles and zeros are lies from the framed value of your given input, by which I can determine my system is stable or not. So this is a gentle transform table we should always remember, because somehow in the gate solution, without knowing the stable values, we cannot set like how ROC can be determined, whether the given system is stable or not. So for that we should always remember, so everything given in the time domain signal is like your discrete time signal here. So all the basic signals are given over there. So initially if you see the first one, it is deals about your impulse, unit impulse signal, and next is about unit step signal. So when we go for Z transform, so any kind of a transform can be applied on the impulse signal will give an output as 1. So if you take Z transform of del of n will give an transformed output as 1, where the value of 1 will remains in all the values of Z in the ROC plot. Okay, and similarly for u of n, unit step signal in terms of discrete plot. So the transformed value can be 1 divided by z1 minus z power minus 1. So this value will be remains same for all the value of z should be greater than 1. And similarly the same unit step signal can be scaled as well as amplitude modulated, so or amplitude scaled value. So here it can be represented by the amplitude is scaled by -1 value and the time can be shifted by -1. So initially the property applied over there is a time reversal because the n values are in terms of minus n, so it can be represented by u of minus n minus 1. So if I want to perform a transformation, initially I should take what is mean by u of minus n, then have to apply minus n minus 1 on the time scale. Okay, so I'll be getting like 1 divided by same kind of values you can arrive for u of n as well as minus u of n minus 1. Only thing is how the ROC limits can be varies. So the value of minus u of minus n minus 1, the transformed value will be 1 divided by 1 minus z power minus 1, where the value of z should be always positive and should be less than 1. And similarly, we'll be applying the shifting on your impulse signal. So m is nothing but the time shifted version of your del of n. So it can be denoted by del of n minus m will be equal to z power minus m. The value of z power minus m remains z power minus m only if z is equal to z is not equal to 0, if m is greater than 0, or z is not equal to infinity where m is less than 0. And similarly, when we multiply some variables along with the step signal, how the transform would be defined. So a power n u of n will be equal to, so same thing in the, if you see for an u of n, so instead of 1 divided by 1 minus z power minus 1, the variable a power n can be multiplied with your z factor here. So 1 divided by 1 minus a z power minus 1, where the value of z should be always greater than value of a, and same can be applied in the third signal where we take z transform. So I'll be getting the same solution as like your a power n into u of n. Only thing is the value of a should be greater than the value of z. So these values are always general. Without knowing these values, while going for inverse transform of any kind of the signal by means of predicting impulse response or output response, the values cannot be arrived. So we should always remember, and if you are not familiarized about this table, generally you can apply all these input signal on the z transform expression by which you can obtain all the solution, where we should describe how the factors of limits can be limited for the given ROC values. And next is about n into a power n into u of n. Already we have seen like a power n into u of n. So if n can be multiplied along with the input signal, so in the denominator factor the same constant coefficient can be multiplied. A power z power a z power minus 1 divided by 1 minus a z power minus 1 the whole squared, where the ROC limit the value of a should be always lesser than the value of z carries. And similarly we will be applying everything. So this table is always general. So if it is a continuous time signal, everything in terms of n can be replaced by t, and the transforms also can differ. So here we will be using z transform, there we can go for Laplace transform or Fourier transforms. So with this we know the solution of all the basic signal, and we should describe whether the given system is stable or not. So system stability can be ensured by means of region of convergence. So generally if you see for Laplace, the region of convergence can be limited by the solution of your given differential equations or your transfer function denominator polynomials values. So by means you may have two solutions. If your limits are lying between those two values, we can say it is stable. If it is beyond those values, then we can say it is an unstable. But whereas here in the z transform, ROC can be described by an unit circle. So if especially in the z transform, ROC can be classified in three different patterns. One is called outer ROC, another one is called as like an inner ROC, and third one is called like an ring ROC. So this will determine by the values of your solution taken by the z transform. Okay, so when we see for ROC, so the region on z planes where the magnitude of h is not infinity, then the magnitude of h of z value should be less than or equal to any constant value, or it should not be equal to infinite. Then if it satisfies this condition, we can say that h of z can converge as a true value which is not equal to infinity. By means we can say it is stable. So other than fetching with ROC, while taking z transform of any signal, you are obtaining some solution. If the solution is not equal to infinity, then we can say it like an stable. Okay, and in other words we can say like h of z exists. So based on the determination of ROC factors, okay, how the ROC can be assigned by the characteristics. So we'll see the characteristics of an ROC here, because when we discuss about any problems, gate problems related with region of convergence, we should know the general solution and what is the condition for an ROC, and characteristics of ROC will help us to find out the solution whether it is stable or unstable. So we should know the characteristics of an ROC. So when we see the characteristics of an ROC, where ROC is always an unit circle at z is equal to 0. So the ROC should be always a circle. Okay, and next is about the poles will always determine the ROC, where the zeros will not give any weight over there. Okay, and similarly ROC is nothing but a region between the values of the poles. There should not be any poles inside the ROC. Okay, and similarly if the ROC is in a connected region, then we can have, as I said, like we have three types of ROC. One is called like an inner ROC, and another one is called like an outer ROC, and another one is called like an ring ROC. So by means of finding the value of ROC, for example, for the given discrete time signal, I'll be getting a solution for two variables. Then I may have two different radius of my region of convergence. So by means I can determine whether my limits are lies inside the first variable or a second values, and this could be determined by three different patterns. So one is like an inner, another one is like an outer, and third one is called like an ring ROC. So next we see about and nature of the signal. Okay, based on first I discussed based on the ROC we describe the stability of the system. Next, the signal nature can be analyzed by an ROC. So first you see, like if it is an outer ROC, then the signal is entirely in the right sided signal, then it is called like an causal signal. Okay, if the ROC is an left-sided signal, then it is called like an anti-causal signal. If you see for a ring ROC, then the limits are lies between those two values, then it is called like combination of your both causal as well as the anti-causal signal. If you have finite length signal, if the ROC is in entire z plane except z is equal to 0 or z is equal to infinity or both, if the lengths are finite, then I can constrain with my ROC like the ROC can be entire z plane where z is equal to 0 or z is equal to infinity are both the cases. So z for a 0 value of z as well as the infinity value of the z, we can have it. And similarly, if the ROC is an inclusive of an unit circle, then the system is stable. The system is stable, and this can be analyzed by using the Fourier transform of LTI system X's, which is called like an discrete time Fourier transforms. So this is the pattern of three types of ROC. The first one is called like an outer ROC. So the values will be lies outside the unit circle, and second one is called like an inner ROC. The value of ROC is lies inside the unit circle, and third one is called like we may have two solutions for ROC, and where my ROC is lies between those two values, we can call it like an ring ROC. So first example with respect to gate solution, we are going to compare the general table and their ROC limits, by which I can come for a conclusion whether the system is stable for the given condition or not. Okay, so we know that h of n is equal to a power n into u of n. From the table you know the general solution. So a power n into u of n is nothing but 1 divided by a z power minus 1. So for this in the denominator factor, if you are equating it to 0, z minus a is greater than or equal to 0. So all the values of z must be greater than the value of a applies. So if you are applying for a is equal to 1, the value should be less than the value of your z value. So ROC will be outside the unit circle. So where alpha denotes your here x denotes your x-axis denotes your poles and y-axis denotes your imaginary parts will denote the poles, and here z is equal to 0, it's a default case, so it can be denoted by 0. Z is equal to 0 condition is denoted over here, and outside the value of a can be plotted. So 0 denotes here, the circle denotes zeros and x plot denotes your pole. So for this the condition, so they will ask the condition for the solution. So the pattern is given like h of n is equal to a power n into u of n. What is the ROC condition? We know the solution of this one, and the solution can be taken like 1 divided by 1 minus a z power minus 1. Again this z power minus 1 can be written like 1 by z while taking a numerator as an z value. So final solution will comes like z divided by z minus a, where numerator will denote zeros and denominator will denotes the poles. So when we equate z is equal to 0, at the point z is equal to 0 we have zeros, and when we equate z is equal to alpha or z is equal to a, where we have an poles. That is what given. So according to the condition for h of n is equal to a power n into u of n, then the ROC limit should be modulus of z is always greater than a. So this is the solution. So the problem will be given by which they will be asking you to calculate the place where the ROC lies. And next is about a second problem. It has to determine whether the given discrete time signals are causal or non-causal. Okay, so according to the sequence given, like h of n is equal to, there are variables and the arrow mark indicated under the variable determines the origin. So for this will be origin 0, and this will be minus 1, minus 2, minus 3, and after this you have 1 and 2. So from this I can able to determine the limits based on the bilateral set transform. So if it is an origin, the lowermost limit is minus 3 and the uppermost limit is 2, and directly I can apply my input signal x of n here z power minus n. So when n is equal to minus 3, so we can apply n is equal to minus 3 over here. So z power minus of minus 3 will becomes z power 3. Then it can be multiplied by 1. So z power 3 alone. Then the second variable is like z power minus 2. When n is equal to minus 2, this will become z power 2. Again it can be multiplied by 2. So it will be z squared again. Then the next variable is like z power n is equal to minus 1. So z power minus of minus 1 will becomes z power 1 plus, next is followed by all the positive values. So by this you can see the convergence rate. Okay, so if I want to find out the convergence of this given discrete time signal, z should take the value except z is equal to 0, because in this factor when you substitute z is equal to 0, z is equal to 0 means z power 0 will become 1, 1 into 1 will become 1. So except the value of z is equal to 0, and rest of the places you can have an transformed value of all the z parameters. So that is what given. So the given sequence we have to determine whether it is causal or anti-causal. So we have expressed the given h of n value in terms of z transform, and we arrive the solution. In this solution, except z is equal to 0, rest of the places h of z exist in z plane, and remaining values are except z is equal to 0 and z is equal to infinity. So the ROC limits are between 0 modulus of z less than infinity. So except 0 and except infinity, rest of the places h of z exists for all the values of z. So if it is so, except to this ranges, your system, the given discrete time signal is always causal. So input is given like h of n is equal to sequence of this, and where the origin is determined by the arrow mark over there. From the origin you can calculate the negative limit as well as the positive limit. After finding the negative and positive limits, we can determine from the solution whether it is causal or non-causal. So while arriving the solution by applying these values in the z and some expression, except z is equal to 0 and z is equal to infinity, rest of the values will have solution. So the ROC lies between 0 to infinity except these values for your z. Okay, this will determine. So other than rest of the values, your systems are non-causal. So except z is equal to 0 and z is equal to infinity, your ROC values can lie. And this could be one of the choice in your gate questions with respect to your causal or non-causal in the discrete time signal. And next example, okay, so from the same table we could go for like h of z is equal to 3 divided by 1 plus 3 by 4 z power minus 1, where ROC they have given like z is greater than the value of 3 by 4. 3 by 4 is given. Okay, so according to the table, like a power n into u of n, while taking the z transform of the same, you will be getting like 1 divided by 1 minus a z power minus 1, where the value of ROC is always greater than a. So h of z can be determined by, instead of a you have 3 by 4 over there. So 3 by 1 divided by 1 plus 3 by 4 z power minus 1 here, and 3 is, we can take 3 common outside, and we are changing the notation into the same like your table conversions, like 1 divided by 1 minus a z power minus 1. So 3 into 1 divided by 1 minus. So if you want to change, make it like minus over here, so I can take minus common outside. So inside you have minus 3 by 4. So if you take inverse of this one, okay, so I'll be having a solutions like 3 into 1 divided by 1 minus of minus 3 by 4 into z power minus 1. So h of n will be equal to, if you go for an input again from the transformation, 3 is constant, where instead of a you have minus 3 by 4 the whole power n into u of n. Okay, so from the given h of z, based on the given ROC, we should determine the impulse response. Generally, the impulse response are we may expect like 8 mark questions or 13 mark questions. Somehow we can manage if it is a multiple choice pattern. We should always remember the table and make the transformation as like a table variable, and go for like look for an input. If it is an input of this one, this might be an solution. So by the way we can arrive. So from the given h of z, I have covered like h of n is equal to 3 into minus 3 by 4 the whole power n into u of n. Since the value of a is minus 3 by 4, so that my solution could be less over there. So accordingly we are changing it, and finally we will be finding h of n is equal to 3 into minus 3 by 4 the whole power n into u of n. So if you are not familiar about the table, what we can do is simply we can apply for So h of z is given by 3 by 1 plus 3 by 4 z power minus 1, and ROC value is given. Accordingly we should calculate like h of n from this, but from the table value we have it like a power n into u of n. While taking z transform, it gives like 1 divided by 1 minus a z power minus 1. But if you are not aware of the table, you can directly apply like your z transform formula. Z transform of inverse z transform of your h of z followed by the inverse expressions 1 divided by 2 pi j and closed contour h of z into z power n minus 1 formula. Or else we can make the solution, or we can arrange the solution accordingly like 1 divided by 1 minus a z power minus 1. If you want to have your transformation like this from the given h of z, arrange it accordingly, and finally we can go for, if it is like 1 divided by 1 minus 3 by 4 z power minus 1, and where this minus 3 by 4 is denoted by the value of a, so I can directly like 3 is common as it is, and instead of a I can write it like minus 3 by 4 the whole power n into u of n. And next example, the same pattern they have given like h of z is equal to 3 by 1 plus 3 by 4 z power minus 1, where ROC modulus of z is less than. In the previous problem, C it is greater than, is given by greater than, and whereas in the next solution h of z is equal to 3 divided by 1 plus 3 by 4 z power minus 1, and whereas the ROC value is less than, ROC value where the z value is less than 3 by 4. So using the table number 6, so which is nothing but minus a power n into u of minus n minus 1 will be equal to 1 divided by 1 minus a z power minus 1. For this solution alone, the value of z is less than the given, the ROC value will be less than the value of a. So ROC is modulus of z is less than a over here. So from the same pattern, the previous expression, however we arrange the term like in terms of 1 divided by 1 minus a z power minus 1, the same pattern we are doing it over here. But instead, where you could see like if the input is like u of n, I can get the solution like 1 divided by 1 minus 3 by 4 z power minus 1. But here the ROC value is less than. If it is less than, definitely we may have a shifting with my input signal, so it can be denoted by u of minus n minus 1. So for understanding this one, we should always remember the table, or else we can apply the values in the exact expression, the Z transform expression, and finally we can come for conclusion what kind of values the h of n can takes place. So h of n is equal to minus 3 into this minus will indicate the polarity over here. So a is nothing but minus 3 by 4 the whole power n into u of minus n and minus 1. So if you are applying this input on the Z transform expression, you will be getting the solutions like 1 divided by 1 minus a Z power minus 1, where instead of a you may have minus 3 by 4. And next is about they have given an is a Z transformed value expressions like h of z, and finally from this they will be asking you to calculate the impulse. So previous two problems are related with an impulse. So first we will see about ROC and where the stability can be retained, and next is about causality and causal or non-causal, how the limits are lying except few values of Z, and now we are seeing about an impulse response. If the transformation is given without estimating any factors, how we can calculate the impulse response value. So h of z is given by 1 plus z power minus 1 plus z power minus 3, where the ROC value is greater than 0, which means that always it is in a positive side. And by the way, you know, like see if the limits are in the positive side, so h of z is equal to h of z is equal to 1 plus z power minus 1 plus z power minus 3, where ROCS modulus of z is greater than 0 over here. Okay, and generally we know that this 1 indicates when the value of n is equal to 0, we can substitute in the Z transform expressions like summation n equal to minus infinity to plus infinity x of n z power minus n, x of n z power minus n, and see here there is no z values, which indicates it will indicates an origin. So where the limits now getting changed, like summation n equal to 0 to infinity x of n, or we can call it like h of n into z power minus n. So in this case, when we substitute n is equal to 0, x of 0 and x of 0 value will z power minus 1, z power 0 will become 1, then x of 1 position will indicates z power minus 1, and x of 2 position will indicate z power minus 2, and x of 3 position will indicate z power minus 3, and so on. So according to the table parameter, so wherever you see, all the factors are nothing but an impulse signal here. Okay, so we can see the table number 4. We are doing shifting on the impulse like del of n minus m, okay, will be equal to z power minus m. So if it is in the case, this first expression, when we go for an inverse transform, this will always indicate, and you know that the solution of del of n is always 1, so which means the signal will indicate where del of n. Next, here if the shifting is done like del of n minus m will be equal to z power minus m. Here z power minus n minus 1 available here, in the sense instead of m you have to represent del of n minus 1, similarly del of n minus 3, and so on. This is how we can calculate the impulse response from the given transformation. And next, the same input signals are given like h1 of n equal to del of n plus del of n minus 1 plus del of n minus 2, if you are taking transformation at a reverse process. Okay, so h1 of z is equal to, if you are taking z transform of del of n will give 1, and similarly one delay in the impulse will give del of z power minus 1, and del of n minus 2 is nothing but z power minus 2. Thus h of z will be equal to, everything can be in the fraction of 2, h1 of z by 2. So we can replace by, since we are doing scaling in the z domain, so scaled by 2 here, so z can be replaced by z by 2, so 1 plus z by 2 the whole power minus 1 plus z power minus 2 z by 2 the whole power minus 2, or else it can be related like 2 z power minus 1 plus, since when we are taking z in the numerator part, it will comes like z power minus 1, and the power is already minus, so can be minus and minus can be multiplied, so it will be z power plus 1, so it can be 2 power plus 1, it can be represented by 1 plus 2 z power minus 1 plus 4 z power minus 2. So this is another pattern how we can scale. So initially we see about shifting, then now we are seeing about scaling. So if the expression is given, if the transformed values are scaled by a factor 2, then how the z transform function can be represented. So this is another pattern. So problem will be given, and they will be giving like a fraction by 2, so all the z values can be replaced by z by 2, then the numerator value can be taken into the denominator, then the power will become minus, already the power is minus, so minus power and minus power can getting multiplied, it will make it like a positive power. So wherever you have a constant variable multiplied by the z variables can be done by n positive factors there. So next example is given in terms of a graphical pattern. Okay, so there are two inputs, x1 of n and x2 of n. This problem is related with the convolution. So if I want to perform convolution of two signal, according to the property, I can take z transform of those two signals individually, then the solution could be multiplied, or else I can apply different properties on both the inputs, then I can do multiply the final solution will give an output. So the two inputs are represented in terms of graphical pattern, like from 0 to 1 I have a polarity of 1 1, and x2 of n can be denoted by the values can be lies between -1 to +1. So y of n, we know that y of n will be equal to the convolution of these two signals. So finally we should find the resultant output into an Z transformed value, so which is nothing but your y of Z. So x1 of n will indicates at the junction z is equal to 0. Z is equal to 0. We have an polarity as 1, which will indicates the del of n. And similarly, this point n is equal to 1, which is nothing but del of n minus m. We have one shifting over there, so it can be denoted by del of n minus 1. Okay, and similarly, or after finding the input in terms of the signal, since it is represented in a graphical pattern, we cannot find what could be the value for 1 or what could be the value for 1 at the point z is equal to 1. But we know that if the values are described in the Z domain and 0 indicates the position, or it can indicate the origin, at z is equal to 0, the value will be equal to 1, then it will exactly represents the impulse signal del of n. And similarly, from 0 to 1 we are applying one shifting, which is nothing but del of n minus m, where m is nothing but 1. So we can represent like del of n minus 1. So after getting the input in terms of signal function, then I can go for an transformation, which is nothing but x1 of z is equal to, when we are taking del of n at z is equal to 0, this will becomes 1, because z is equal to 0 means z power minus n is equal to 0, the value will be 1. And similarly, when n is equal to 1, z is equal to the power of the z will carries the positive value, already z power minus, so it will be 1 plus z power minus 1. And similarly, from the second pattern, I have taken a transformation of x1 of z, then I can go for x2 of z now. So I want to find out what is my x2 of z, and this will indicate if it is positive side, we can represent it like an del of n minus m. If it is in the negative side, I can represent it like an del plus. So this, for this limit -1, my signal function will be del of n plus 1. At del is equal z is equal to 0, it will becomes 2, which means 2 can be multiplied by a scaling factor of del of n function. So similarly for 1, del of n, we have a shifting for the positive side, so it is del of n minus m. So del of n minus, instead of m we have a value as 1, while taking the transformation of this one. So here n is equal to, when you distribute like n plus 1 is equal to 0, n is equal to minus 1. So z power minus of minus 1 will become z power 1, so it will be z. And similarly, 2 into z power n is equal to 0, here z power 0 will become 1, so 2, then followed by n is equal to 1, z power minus of 1 will become z power minus 1. So now we know the z transform value for the given graphical representation into signal, then into z transform, and similarly x2 can be in terms of signal, then into an z transform parameter. So if I know the transformed value of those two signals, finally the solution can be multiplied of those two transformed values. So the first transformed value is 1 plus z power minus 1, and second value is z into z plus 2 plus z power minus 1. So you can multiply and arrange, finally you will be getting y of z is equal to z plus 3 plus 3z power minus 1 plus z power minus 2. So these are all about the general problems related with your Z transform and its ROC. And next session we'll be seeing about how the inverse Z transform will be employing and how the system characteristics can be identified with respect to output response, impulse response, natural response, and forced response. So most probably all the transformation we should always remember the basic table. So with this we can close the session and we can see the remaining part by the upcoming session. Thank you all.